we'll be needing quite a few Python libraries in order to perform EDA. So what are the libraries that we'll be needing? We'll be needing OS, Pandas, NumPy, Matplotlib, and Seaborn. Okay, so we'll first import these libraries. So that's the first step. And then we will import our data set. Our data set has been kept in this particular path. So I'll define this as a working directory so that we can also save our output in this particular path. Okay, and our data set is already there in the path, right? So where you have your import data, it's better to define that as a working library so that in the same folder you can always keep your output as well. chdir, and we'll simply be needing the OS library. Okay, that's the way we define the working library, and we'll run that. So working library is now defined. So once the working library is defined, you don't have to explicitly mention the path while importing the dataset, because now we are already in that particular folder. So we'll simply be importing the dataset from that folder, and the dataset is already there in that folder. Okay, so we'll be using the pandas to import the CSV file. The data is in CSV file. You can also import other forms of data like flat files or even Excel files and so on. We'll use read_csv method in order to import the CSV file. Okay. Now here you can see the pandas has been imported as PD, right? So henceforward, instead of pandas, we'll simply be using PD. Instead of NumPy, we'll be using NP. For Matplotlib, we'll be using PLT, and for Seaborn, we'll be using SNS. So pandas is basically for handling of data. NumPy, on the other hand, doing some basic numerical computation. And then Matplotlib and Seaborn both will be using to do various plot, right? To visualize data, we'll be using Matplotlib and Seaborn. All right, so we have we'll now import the data. We'll run the code. Now the data has been imported, and let's just see. So we're importing and saving in a data frame called cars. Okay, so data frame is basically just a two-dimensional form of data, like the data you see in an Excel sheet or a spreadsheet. That's the way we'll keep it, right? So it's just a two-dimensional form data. We have a fancy name called data frame, right? So that's the way we call this. Okay, so what's there in cards or the data frame that we just created using importing the CSV file? So we'll use the head method in order to see the top 5 observations, and let's run this, and we can see the top 5 observation in our dataset. This dataset is called cars dataset. It has the information about different cars, the make of the car, the model, the type, the origin, the price, engine size, number of cylinders, horsepower, mileage, weight, wheelbase, and length. So there are quite a number of features that we have in this dataset. And we can use this dataset for various reasons. We can do a segmentation modeling using this. I have shown you in another video how to do segmentation analysis using this particular dataset, but using R. Simply be doing exploratory data analysis without building any model in this video. Okay, but we can of course use this exploratory data analysis before all kinds of data analysis or statistical modeling that we do. So these are some of the basic steps that we need to follow before building any model. Now that we have the data and we can see the data by ourselves, but we can only see the top 5 observations, right? We can of course see the entire set of observations, but it's difficult to sort of understand simply by looking at the raw file or the raw observations, right? We need to summarize them in some form in order to get some basic insight out of this data, right? That's where the EDA will help us in great deal. So we'll also see the information about the data set, like the data types and so on. So we'll use the info method in order to see. So we'll run this. So cars.info is going to give us like the types, the data types of each variable and so on. Okay, so we have, let's say here, engine size is just float, horsepower is an integer, right? So these are some basic observations. If there is some mismatch, we can of course change the data type. Okay, if we want to change the data type, that also we can do, but before that we also need to know what is the data type by default that Python is assigned. Okay, for instance, we do not want a certain number of variables. For instance, here we do not want the price and invoice price, the retail price and the invoice price. We simply want to get rid of. We simply want to drop them from the variable. How do we do that? Okay, so we'll simply first define a list. So here is a list, some form of array, where we define these variable names MSRP and invoice. Okay, and then we'll use the drop method. Okay, so we'll use the drop method in order to remove this or drop these two variables. Okay, so here is the list drop underscore columns. It has got two variable names, and that's exactly what we are using as the parameter to this method. And what it's going to do is simply going to remove or drop these two variables. Okay, now we have run it. You can see whether we actually have. Okay, so let us run the above code again, like cars.info now. I'm sure you will see that the two variables are no more there in the data frame, and that's what you can see, right? We do not have MSRP, neither we have invoice. So we have been able to get rid of both variables. All right. We can also draw rows, and oftentimes what happens is that we come across duplicate rows, and duplicate rows are not good for analysis. We need to get rid of these duplicate rows. Okay, so duplicate rows are basically rows which are just repeating. There's no additional information. It's the same of information repeating more than once. How do we do that? We can get rid of the duplicate rows for all columns at once, right? We don't have to do any iteration as such. So how do we do that? We'll use the method drop underscore duplicates. Okay, and all we need to do is that we need to simply give keep underscore first. That means we simply select the first observation and remove the others, right? Given that the row is duplicate, it doesn't actually matter whether which row it actually selects or keeps, and which other rows it deletes. But we'll simply define this in order to keep the first one also. Otherwise, it simply by default also keeps the first one and removes the others. All right, and our data set doesn't have duplicates. That's what I already know. But in case you have duplicates, then this is very useful. It takes out all the duplicates rows from this data set. Okay, now we'll see what is the size of our data set, like how many rows and how many columns do we have in this data set. We have 428 rows and 12 columns. Okay, so that's basically is the size of a data set. And how do you get to know? Use save, cars underscore save. Cars is our data frame. Just use the save, and we'll get the number of rows and the number of columns. Okay, and then what we'll do is that we'll perform some basic summary statistics. And how do we get the basic summary statistics? We'll use the method describe. Okay, cars underscore describe. When you do that, you will get the basic summary statistic like mean, median, standard deviation, and so on, right? And that's what you can see. One thing to note here is that you cannot get mean, standard deviation, or maximum and minimum for categorical variables. You only get for numerical and continuous variable, right? Continuous numerical variables, right? So in this you can see the count, the mean, standard deviation, the minimum, and the 25 percentile, the 50 percentile, 70 percentile, and the maximum values. Okay, now the basic summary statistics help in a great way to understand the distribution of the data. Okay, for modeling, make sure that the standard deviation is not zero. If the standard deviation of a variable is zero, then that variable gives us no variation. There's no variation in that data, and it's not very useful for statistical modeling. So we simply need to get rid of that variable or drop that variable from the analysis. All right, what else? Well, looking at the mean, the minimum, and the maximum, and obviously the percentile distribution, we'll get a feel of whether the data has outliers or too many extreme values, and so on. Sometimes we have extreme values that are unacceptable. That means they will create a major trouble in model building. So we need to just get rid of these values. Okay. So identification of outliers, missing values, and so on require us to do some basic, this summarization. Okay. If you really want to sort the variables, sort the data with respect to variable, just to see, extreme values in bit more detail, right? Because here, when we summarize, we probably won't get to see the extreme values too closely. Okay. We want to see little more at a little more granular level. We can use the sort underscore values methods. Okay, so this method we can use in order to sort the variable with respect to a given sort the data with respect to a given variable, and we'll be sorting with respect to mileage. Okay, assume for instance that this is the variable of interest. This probably is going to be the target variable in our modeling exercise. Let's assume in that case we'll simply do a sorting of this data set with respect to the mileage, and we'll sort by descending order. We can of course sort by ascending, but we'll do it in descending order. So the maximum, or the bigger values will be at the top. Okay, and let's run this. Yeah, so this as expected is giving an error. And why is that happening? Is because there is a space, blank space in the column name mpg. The column name mpg is having a space, extra space. Okay, so we have now an extra space, and it should work now. Now it works, but we don't want that, right? We do not want this space to remain with mpg, because it looks really odd to have a space as part of a column name, right? We'll need to get rid of this particular space. And how do we do that? We need to use string dot replace in order to replace the space, unwanted space from each columns. Okay, so here is the syntax. Cars is the data frame. Cars dot columns is equal to cars dot columns dot str dot replace, and we are replacing the unwanted space. Okay, now we have remove the unwanted space. So let's run the original code, and we hope that it works. Yes, it does. You can see the data is sorted with respect to mileage, and the bigger numbers are at the top, so it's sorted in descending order. We do not have too many outliers in our data set, too many extreme values in our data set, because this is most a very well structured data set, publicly available data set, so we wouldn't have it. But in real world we'll get to see the extreme values, and we can simply remove them once identified. The next thing we'll do is that what if we want to do it dynamically? That means instead of looking instead of simply sorting the data with respect to ascending order and descending order, and then doing it for each one of these variable, we're doing it, or we're running the code too many times. So can we write a function which does it? The function is used in order to automate something, right? In order to do something repeatedly, but we don't need to write the code. We simply have to call the function. So here is the function where we will get the minimum and maximum values of a given variable, and we simply pass on that variable name, and it's going to give us the minimum and the maximum values. We can get, of course, top 5 and bottom 5 values as well. How do we do that? We define the index first, like the top index, and the idx max method is going to give us the top index of the data frame with respect to obviously the column name. And similarly, idx mean will give us the bottom index. Okay, and we'll use that with the help of loc function in order to extract the minimum and maximum from the data frame for that given variable. Okay, and then we combine them, we concatenate them using pandas concatenation method, and then that's what is being returned by the function. So let us run this function, and then let us use this for mileage. Okay, we'll use this function for mileage, and here you can see the minimum and maximum and the associated values. Like it's not just the minimum and maximum um, of mileage, it is also the associated values of other variables or other columns, right? And that's what you can see here, right? We have make, model, type, origin, and so on. So we don't get that in a summary statistic, do we? No, right? We simply get the minimum and maximum. We don't get the associated values or the corresponding associated values of other variables for that minimum and maximum value. We can do that for length. We can do for any kind of continuous numerical variable. So here is for length. Minimum is 87, maximum is 238, and we have the make, model, type, origin, and engine size, and so on. Okay, just to confirm whether it is correct, we'll go to the summary statistics. Just to confirm whether it is it is the index or is the value. Okay, just a moment, we'll go back. For length, max is 238 and minimum is 143. So it's not the values, it's the index. That means at the 87th number row you have the maximum, and 238 we have the minimum. Okay. Okay, just to confirm, we have used the maximum first and minimum second. That's right? So maximum first we took, and then minimum second. Now the order could make a difference, so that we need to ensure. So the maximum is happening at the index 87, and the minimum is happening at the index 238. And the values are simply in front of us when you print. Once that's done, we'll see some visualized form of data analysis. We'll plot the histograms of the continuous numeric variables. And how do we do that? We'll use the matplotlib. So plt.histogram. So hist method from the matplotlib is going to be used in order to create this histogram. Histogram is just a visualized form to see the distribution of continuous data. And we'll have 10 beans. You can have as many number as you want. So we'll do it for a mileage. Okay, and there are two parameters. First one is the variable for which we want to create histograms, and the second is the number of beans. Okay, you can replace that with simply with 10, right? Instead of providing as a variable, we can simply hardcode the scalar value as well. So we'll run this, and here is the histogram. It has got 10 bins, and this is the distribution of mileage. Okay, there can be several distribution, right? Distribution in the form of histogram is just a data distribution, and we are simply summarizing data with each bean. Okay, in summary statistic, we simply have just one bean, right? Which is centered around the mean, or centered around the median, or the the maximum or the minimum. But here we have 10 beans, so you have distribution at different section of the data, and that's much better to understand rather than the basic summary statistics. You can see that to the right you have, if you look at the cursor, there's some observation even at 50 and 60. Okay, and that's they are typically the extreme value. So we have fat tail, right? So fat tail is just a case when you have some observations very away from the other observations. So you can see my cursor, these small set of observations, maybe a few only, but they are totally different from the other set of observations. So they are extreme to the right. In statistics, we call them a typical case of a fat tail distribution, and we can remove them if we if we're going ahead with any statistical analysis. We can overlay the probability density function also with respect to the histogram. So probability density function will ensure that we get it in percentage terms rather than the actual values. Here we have the actual values, right? The actual summarized value of mileage in each bean, right? For the first, and let's say we have 25, second we have 175, something like that. But here for PDFs or the probability density function, we would be having the percentage terms, right? And the area under that PDA is always going to be 1. So that's the constraint of a probability density function curve. And here is the PDF curve. You can see all of them are in percentage terms, right? It has to lie between 0 and 1, and it does lie between 0 and 1. If you take the area under this particular curve, you will get it as 1. As I was saying about the fat tail distribution, you can see the tail is quite longer in the right hand side of this curve, right? And we need to simply remove these extreme values, and then it will look somewhat normal, somewhat bell-shaped type. Okay, and that's what is an ideal data for data analysis. We'll do that for other continuous variables like length. For instance, yes, the distribution of length looks much better than mileage. There are hardly extreme values. There are hardly the distribution is hardly long-tailed. We can also have the probability density function for this. All right. Now we will see how we can do cross-tabulation for the categorical values. Like for categorical values, we cannot obviously do the summary statistics, or we cannot do histograms or a probability density function and so on. Right, that won't make sense. But we can do the analysis just by taking the count in each category for a categorical variable. So that's basically known as the cross-tabulation, right? Cross-tabulation is of course with two variables, but not going by the definition of cross-tabulation. We simply sort of take the count. Okay, I'm calling it as cross-tabulation, but don't take it by definition, right? By definition it's somewhat slightly different. So we'll use the group by method, and group by we will it will count the number of observations with respect to the different categories for a given categorical variable. Make is a categorical variable, and we will compute, or we will calculate the number of observations for each categories. Okay, how do you do that? Group by and then dot size. Okay, we run this and then we will see what's there. So here we go. We have make, and for each make we have the count or the number of observations that falls in a given category, and that's what we have in front of us. Okay, we can also plot the distribution. We can plot the distributions to various ways. We will use something called Boxplot, and obviously bar chart is something that also can be used for showing the distribution of categorical variables. We will use some of them. Okay, so so let's plot. Okay, so we can use the plot. Okay, the method in order to plot the variables. Okay, so make distribution. So make underscore dist is coming from the previous code. Okay, so we have already defined it, right? So we have defined it does have the count, and we're simply plotting the count. Okay, so count obviously is a numerical value, so this numerical value is simply plotted here. Okay, and the title you can just give any title. I'm just given make distribution. Okay, you can give any title here, and here you see the distribution of the count with respect to, and visualization helps us in order to see whether a particular type of a given categorical variable is dominating that particular variable, right? It helps in sampling. Actually, in sampling we ensure that the observations are well represented, or sorry, the categories are well represented in the data. There should not be too many observations for a given category or too less observations for a given category. Then that's not a good thing for statistical modeling, something that we avoid. And then we'll do it certain things for all numerical variables and for all category variables. So we can do that. We'll first select all numerical variables. How do we do that? We use the select d type method, and we will select the data types float and the integers. So these two data types are basically the data types of numerical variables. So it will simply select these data types. So in essence, we'll have the numerical variables in this particular list. Okay, and we call it car_num. That means numerical variables in the cars data set. That's exactly what we mean, and then we'll print obviously. So what are these variables? So we have engine size, horsepower, mileage, weight, wheelbase, and length. So these 6 variables are the numerical variables in our data set. Okay, and we have combined them and we have put it in a different data frame, and then we will do some sort of analysis on these numerical variables, something that we cannot do on categorical, like histogram. We cannot do histograms for categorical variables, right? So so this section is where I'm going to show you where you can do analysis for more than one variable. Instead of doing histogram for just one variable, how do you do it for a number of variables, all numerical variables? So here we have all numerical variables in this particular data frame, and then we'll call this hist method, and we'll define the beans. Here we define the beans as 20, and we'll see the histograms for all of these 6 numerical variable just by running one line of code. It's going to take some time, but we'll have, yes. So here is the plot, and it has the 6 histogram plots for different variables: engine size, horsepower, length, mileage, weight, and wheelbase. So in just one go, we are able to create this beautiful plot. The next thing we'll see is the correlation. Correlation is actually a relationship between variables, and we compute that for numerical variables, not for categorical variables. So that's something we only can do for numerical variables. Now there are 2 ways we can do. We simply take 2 variables at a time and then take correlation of them and then keep on doing that, or we simply take the subset of the all numerical variables and compute the correlation matrix. We'll do the second thing. That's easier, right? We do it in just one go. How do you do that? We will take the car underscore data frame that we had created, the subset of variables which are numerical variables from cars dataset, and then we'll use the core method, which is going to compute the correlation for us. And the variable with which we'll compute the correlation is mileage. Okay, let's assume for a moment this is our target variable, and we want to know the correlation of the other variables with this target variable. We expect them to be very high in order for these variables to be useful. If the correlation is very less, then probably the variables are not going to be useful. Right, so that's basically is what we want to see. We will run this code and then we will see the correlation, and here we have the correlation. We have strong correlation for most of the cases. As expected, the correlation between mileage with mileage is 1, right? Correlation with the same variable is always 1. Correlation also gives an indication about the direction in which the relationship are, although it is not quite correct to conclude, but it gives some preliminary indication that there is either there is a negative relationship or there is positive relationship, and wherever you have negative sign, you have negative relationship. That means one increases, the other one will decrease, and when we have positive sign, both increase simultaneously. Well, we can also see the correlation in visual form. So we can plot the correlations, and we'll use the pair plot from the Seaborn package that we had imported initially. We'll use pair plot from there, and we will plot the correlation for all of these numerical variables with respect to mileage, because that's the variable of interest or the target variable. Okay, we'll write a loop. Okay, and the loop ranges from 0 to the number of columns in the new data frame that we have created, cars underscore num, which only has the numerical variables from our cars dataset, and then we plot it, right? So for cars underscore name, this is x, so each of these variables will be in the x, and we also define what is going to be y, which is a fixed, right, mileage. Okay, sorry, so this is the data set, this is the data frame we are providing, and here we have the index x, y, and x indexes, like what we want to keep in x and what we want to keep in y. And obviously x will iterate through this loop. Well, it is going to change, and y is constant because we want to see it for with respect to mileage for each one of these other variables. So we have run it, and here are the correlation plots. As you can see, most of them have negative relationship. That's exactly what we had seen in the previous run. See, there's a negative relationship, and here also we see negative relationship. If it is downward sloping, then negative relationship. If it is upward sloping, there is positive relationship. Plot between mileage with itself is something we should not even interpret, because that makes no sense. It's just have a one-on-one relationship. So we won't interpret this one, but the other ones are very useful. And you see whether there's a strong relationship, there's a weak relationship. Like a mileage with length has got slightly weak relationship, or weaker relationship, because the variance is higher here. But if you see here, like weight, it seems to be a much stronger, although we cannot conclude like that, but at least it gives us somewhat an indication. um, yeah, and also these plots are useful to locate extreme values. Like, as you can see, some of the values are extremes, and we also had seen these extreme values in other analysis, and then this simply confirms our observations from other analysis, so that we can remove maybe 1% of the extreme values, or 1% of the observations which can be considered as extreme values from the data before doing any statistical modeling. Yeah, now we have, for instance, let's say we have too many independent or too many features. Now plotting them is a bit time consuming and also a bit difficult, so we can plot more in heat map forms. Like wherever we have a significant correlation, it's going to appear in that heat map. Okay, so we'll use the heat map method from the C1 package. And there's few things to mention, like how it should look and how it should not. But we can define the threshold. Like I'm defining the threshold, like anything greater than 0.5 is a significant correlation. Now it's not a thumb rule. Sometimes we can take variables till 0.6, and sometimes we remove variables which are even greater than correlation greater than 0.4. So it is a bit subjective, but we have used 0.5. Okay, now correlation with the target variable is always good. So the higher the correlation, the better is the variable, right? But that's not the case with the independent features, right? The correlation, high correlation is not a good thing there. So we can have this heat map separately for target with other independent variables and within the independent features. So that way, that's the way we can select and remove some of these variables as well. So it helps in terms of feature selection as well, the basic feature selection, obviously. And here you have different colors, but you see the colors are there only where you have correlation of greater than 0.5. Other cases it simply comes white, right? These cases where there is no relationship, because there's no coloring here, because the correlation is less than 0.5, and that's the threshold that we have set up. We do have is 5-6 variables here, so it's not very useful, but in case we have, let's say, 50 or 60 variables, this is extremely useful in this form. The last thing that we'll see is we can visualize categorical variable data using Boxplot. Okay, so Boxplots are very useful to locate extreme values firstly, and also making inference about the distribution of data around its mean. Okay, an ideal box plot that we would expect from variables is that the data is equally centered around the central tendency, mean or median. Okay, so we'll use the box plot from the C1 package, and we will do. So this is where we'll do, like, for each type. So type is a categorical variable in our data, and in the y we'll have mileage, which is the variable of interest here, right? So we want to know how the average value of mileage with respect to each type, and if I run it, it is going to be much clearer. So here we see we have how many types. We have 6 types: SUV, sedan, Ford, sports car, wagon, truck, and hybrid. There are 6 different cars type, and we want to know the mileage with respect to these types. And we see hybrid is much ahead or much higher than the other types. The other types are more or less the same. The average mileage is more or less the same, but hybrid it is very different. And also we can see the distribution, like there is more variation of the mileage in sedan and in wagon, but there is much less variation for SUV, sport car, and truck, right? So these are some of the insights that we can get out of this box plot. We can do the same for other categorical variables also, like let's do it for origin. Here you see the mileage with respect to origin. That means whether it is the origin of the car, like where the car was manufactured, whether it's Asia, Europe, and US. You see the mileage, the difference. They're more or less the same. Slightly in Asia it is more, but otherwise they're pretty same. We can we can do the same for other categorical variables as well. Okay, so that's another way of visualizing data, or doing a bit of exploration about the data that we have. The final thing that we'll do is the regression plot. Now, regression plot derives its name from the regression analysis, where we're basically trying to see how one variable is related to the other variable. And both the variables have to be numerical variable, not the categorical one. Okay, and it gives us insight about the direction of relationship, whether there is strong relationship or weak relationship, and it helps us in selecting good variables and removing bad variables. Okay, when I show you the plot, you will be able to understand how it actually helps. We'll use the C1 package, and we'll use the rate plot from method from the C1 in order to do a regression plot of length and mileage. So mileage is going to be our y, and length is going to be our x. Okay, so here is the regression plot. So the difference between a correlation plot and a regression plot is that we have a regression line here. So we have a least square line which passes through the middle of this data points, and that helps in many ways, right? If most of the data points are lying very close to the regression line, then it is a good variable. That means there is a strong relationship between these two variables, right? There are few observations which are lying very away from them, but they are outliers or extreme values as we had identified, and once we remove them, the relationship looks much better. But imagine a case where the regression line doesn't pass the middle of these data points, and the data points are simply distributed very ununiformly across this regression line. In such a case, the relationship is not very strong. So that's one thing we conclude. And this is some sort of a bivariate analysis which helps us in order to get down to the most important variables for